Hello everyone. Our project is Templatized floating point arithmetic unit for high-level synthesis. It focuses on designing a flexible and efficient floating point unit using HLS. This work was completed as part of the high-level digital design automation course at Cornell University. Let's get started. Traditionally, floating point operations use IEEE standard. However, for deep learning, reduced precision formats like bfloat16 and FP8 have emerged as effective alternatives. These formats balance accuracy and cost, making them well suited for tasks such as CNN training and inference. As shown in Figure 1, reduced precision formats achieve significant hardware efficiency by simplifying the representation of floating point numbers. For example, FP8 reduces both the exponent and mantissa size compared to IEEE standard, enabling faster and more efficient computation. To further optimize floating point operations, Fuse designs combine alignment, normalization, and rounding into a single operation, reducing computation overhead. Building on this idea, our project develops a templatized floating point arithmetic unit. In this project, our design supports customizable floating point data types, including 8 bits, 16 bits, and 32 bits formats. It is flexible for different application requirements. Our arithmetic unit includes core functions such as addition, subtraction, multiplication, multiply accumulate, and dot product, which are essential for tasks like deep learning and signal processing. To evaluate performance, we incorporate the Cordic algorithm to compare latency and resource utilization against standard IEEE floating point implementations. Additionally, we focused on optimizing the dot product operation, which is a critical component of many vector computations. By leveraging HLS features such as loop pipeline and unroll, we achieved a balance between hardware efficiency and accuracy across different floating point formats. First, I'll start by introducing the implementation and optimization of. This table shows the experiment results. The results show that our design.
Okay, now let's talk about the design and optimization of the multiplication operator for the templatized floating point. Figure 3 shows the architecture of the multiplication unit. Each input is represented by 3 parts: sign, exponent, and mantissa. The sign bits are preceded using XOR logic. Exponents are added together with the bias adjustment. The mantissa are multiplied in the multiplier unit to get the results. Also, the normalization is performed on the result, followed by rounding and overflow handling to ensure correctness. This multiplication unit is optimized for performance and efficiency. The use of loop is avoided to enhance hardware efficiency. The subnormal number handling is removed to reduce complexity. The bit widths are also parameterized, and the width of the intermediate variable is minimized. Here shows the evaluation results of single multiplication operator for different floating point data types. The table compares 6 data types in which floating 8, mini-float, bfloat, float 16, and 32 are generated by our templatized floating unit. Xilinx float shows multiplication performed using Xilinx internal floating point IP core that we want to compare with. As you can see in the table, our templatized float could achieve almost the same accuracy as Xilinx float when using the same bit widths, and increasing mantissa bits can reduce the root mean square error, but will increase the hardware utilizations and latency. Floating point 8 and mini-float, which are generated by our templatized floating point unit, consume minimal hardware resource and latency, but result in higher errors, making them suitable for resource-constrained environment with acceptable error tolerance.
Figure 4 shows the architecture of the fused dot product design organized into 5 stages: multiplication, alignment, addition, rounding, and normalization. The computation follows the tree structure split into 4 steps, where the design suggests a 4-level pipeline structure. The actual pipeline is determined automatically by HLS based on the constraints set by the designer. For example, we can generate error-efficient single-cycle design or high-speed pipeline design without changing the hardware model. The process begins with unpacking the n pair of floating point inputs. The unpacking stage inserts the hidden bit into mantissa to create a fraction for each operand. This fractions are forward to multiplication units since their design targets deep learning accelerators. Subnormal numbers at their input are flushed to zero to simplify the computation. This approach ensures a balance between precision, efficiency, and hardware requirements for deep learning workloads. Okay, this table compares the performance and the resource utilization of the fused and non-fused implementation for dot product operation across different data types. The non-fused version implements the dot product using separate custom multiplier and adder module. It can lead to extra rounding between operations, but the fused version integrates multiplication and addition into a single operation. It can avoid unnecessary rounding and improve precision and performance. And we can see the fused implementation achieve lower latency, reducing cycles to as low as 8 for FP8 mini float and B float. It also has higher precision with RMS error rate coming close to those of the standard float for larger bitwise taps, while the fused version slightly increase LUT usage. It saves flip-flops compared to non-fused design, showing efficient resource trade-offs. Overall, the fused implementation provides a balanced and optimized solution, achieving comparable performance to silenced float with reduced DSP usage.
After designing and evaluating the single operator, we move on to testing our operator under a real workload. For this, we utilize the codec algorithm to compare the performance of the silenced float and our templatized floating point unit. The codec process involves a series of additions, subtractions, and multiplications, making it a good benchmark to verify the functionality of the operators we developed for templatized floating point. Now let's introduce the codec algorithm. It is an iterative approach for computing trigonometric functions. The key idea of the codec is computing the target values through iterative vector rotations. As shown in the diagram, the process starts with an initial vector. The algorithm applies successive rotations, each one moving the vector closer to the target angle beta. The final vectors x and y components represent the cosine beta and sine beta respectively. Additionally, there is a magic equation that represents each iterations. It demonstrates how the vector is updated using a scaling factor ki. Now, let's talk about the testing of the codec algorithm. This slide represents the architecture and testing approach for a codec accelerator implemented on the FPGA. The testing uses three types of data representations: fixed point, floating point, and templatized floating point. Fixed point is also included because it is also the most efficient option for codec applications. Fixed point arithmetic reduce latency and make codec ideal for many real-time applications. The system consists of two components, the FPGA-based codec accelerator and the ARM processor. The codec accelerator will determine if the rotation should be positive or negative, and it saves the time to cosine value. It will then perform the rotation to compute the new theta. And the data flows through the FIFO buffer between the FPGA and ARM processors. Values from host program are translated to AP onsite 32 to feed into the buffer. Here is the results and evaluation of the codec algorithm. The table shows the results of implementing codec with different types. The analysis highlights 4 key points. First, all design can achieve high accuracy with 8 bits for the exponent and 23 bits for the mantissa, making it suitable for precision-critical applications. Second, formats with limited bit widths, such as B-float, demonstrate better performance and hardware utilizations, making them ideal for resource-constrained scenarios. Third, as precision increases, hardware usage grows significantly, shows a clear trade-off between precision and resource requirements. Finally, fixed point stands out by delivering the lowest error and latency, making it an efficient and reliable choice for coding computation where accuracy and speed are critical. Here is a short demo for the coding program using our templatized floating point arithmetic unit. Here is a short demo to show our design runs on the FPGA. I'm now in the folder of codec myfloat FPGA, and I want to run the codec design using the 16-bit spring float defined by our myfloat class. The bit stream is already bounded to the SD card, and we can now run the batch host. It will show the result we got for the codec algorithm using the 16-bit spring float format. These are the root mean square error in percentage. So this result indicates the sine and cosine calculation got the 2.6% and 1.5% error respectively, and it matched the expectation of using bfloat in the codec algorithm that we've discussed before, and it used a time around 5.3 milliseconds totally. So our templarized float point is proven to successfully work on the FPGA. All right, that's all of our presentation. Thank you guys for listening.